Okay, we have a reactor where we're adding this material and reacting it with aluminum and lime. And these are our products here. So the question asks us to find the masses of aluminum and lime that should be added, as well as the mass of this that's formed, and then this other question about using excess lime, what would the composition be? So let's go ahead and let's actually start with a process flow diagram so we can get our mind around what's happening here. Okay, I'm going to go ahead and create the drawing, and I'm not going to make you suffer through my drawing of it here. Okay, here's the process flow diagram, and one of the things I want to point out is that we have kind of a dilemma in the problem because it gives us kilograms here, and our biggest clue in the problem is that, let's see, for a stoichiometric process, what are the masses that should be added? So we know that stoichiometry is really based on the chemical reaction, and so we're going to have to work at the level of atoms and then work back to mass. So let's go ahead and set up our problem in that way. Okay, you can see this is how I set up the table, and I want to point out a couple things. At the top here, we're looking at the streams, and we're counting. Well, we have different ways of counting the streams, so we're going to have to keep our head in the game, knowing that we can count atoms of the streams here, and that would be one kind of conservation equation, or we can count mass. We know that mass in is equal to the mass accumulated. I took the liberty of writing the molecular weights for all the different components here, and let's go ahead and fill in this table for each component. Now remember, for aluminum, or actually for all of them, we're just going to, on this line, but component by component, we're going to write down an equation. So if we're looking at counting moles of these components for aluminum, we know we have A moles of aluminum. So we would just put the letter A here. Let's see if I can do that. We would have A here. And let's see where else is that aluminum distributed. We have no aluminum here, none in this component. We've got some here and some here, so we have to make sure we account for the number of aluminum atoms in each component. So for this case, we would have X molecules of Nb3Al times 1 Al per molecule. In this case, we have Y molecules of Al2O3 times 2 atoms of Al per molecule of Al2O3. And we're going to go through, and there's no aluminum here, so we'll go through with each line and make sure we account for each one of these components in the same way. Okay, if I were being super careful about the units, what I would do is keep track of them. So for example, in calcium, again, we're going to write on this line right here, it's going to be accounting for each calcium atom. So there are no calcium atoms in aluminum, and we'd have B calcium oxide atoms or molecules, and one calcium oxide molecule will give us one calcium atom. And then down here we have Z calcium fluoride molecules, where one calcium fluoride molecule gives us one calcium atom. And you could see that I've used the orange to kind of do a kind of dimensional analysis and just essentially to indicate, for example, with oxygen, B calcium oxide molecules, each molecule yields one oxygen atom, whereas here each molecule of niobium oxyfluoride gives us, two atoms of oxygen, and then over here each molecule of Al2O3 provides 3 oxygen atoms. So that's the thing that we're adding up on each one of these lines, is the number of atoms of each. So then we begin to balance this thing in order to get a in order to get our stoichiometric ratios. Let's rewrite these equations now. Maybe I'm going to get rid of some of this so we can see this a little bit more cleanly. Okay, so what I've done is I've gotten rid of a lot of the words here, so you can just see the equations. And as you can see, we have way more unknowns than we have equations. We have 1, 2, 3, 4, 5 independent equations, and we have 1, 2, 3, 4, 5, 6 unknowns. Well, not way more. So it looks like basically we can pick one of them. We can select one of them and then begin to solve it. So once we choose one, we'll have 5 unknowns and then 5 equations. So I'm going to do something kind of funny. I'm looking at the numbers here, and what I know is some of these are going to lead to fractions like this, knowing that there's 3 in here, 2 over here. So I'm going to do something kind of funny. I'm going to make that x a 2, and then I'm going to start to work backwards. So if that x becomes a 2, then I can get the value c. Once I have c, then I can get the value z. Once I have those, now I can z, I can get b. Then I have now b and c, I can get y. Y gives me this y here. I already know x, and then I can get a. So once I choose x as a value, it starts cascading so that I can create a solution. So I'm just going to start there. I'm going to choose x as 2. So now that x is 2, I know that that c is equal to 6. If c is 6, I know that z is then 3. So we've got 3 up here. So b is also now 3. 2 times 6 is 12. So 3 plus 12 is 15, which is 3y. So I know that y is equal to 5. So this becomes 10. 10 plus 2 is 12. So a becomes 12. So that becomes my my new stoichiometric equation. Let's see if I can simplify it any. So we have 12 aluminum plus 3 calcium oxide plus C, which is 6. See, X is now 2. Y is, what is Y? Y is 5. And Z is 3. Okay, there doesn't seem to be like a common factor in here. We could divide it all by 2 and make it simpler, but this is good enough for us. So this is our stoichiometric equation. And let me clean that up.